Share. All right. Pretty good. When I check the audio, it's usually right. It's right. Okay, so we're online for anybody. It may show up 3 people already. Okay, so some people have found it. Good. All right. And I'm going to open Twitter as I have before for you online people. If you have a question, especially if something is wrong, like you can't see the screen or something, please tweet me, and a message should pop up on my screen, which I may see. As close as I can get to having some kind of feedback. Oh, another thing someone told me last week is that the online people have their microphones on and they're making noise so they can't hear things. I found a way to fix that, mute everybody. I don't know if I can figure it out again. I'll manage participants perhaps. Mute all, there we go. All right. All new participants are muted. I hope that doesn't mean I'm muted. Am I muted? Maybe I am. No, I'm not muted, it seems. I see the microphone. Okay, good. So hopefully that will stop you from bothering each other with chatter. But anyway, if something comes up, send me a tweet, and hopefully it'll pop up and I'll see it. Anyway, so that's the future. Next couple of weeks are set up there. And let's take a look at news. A few minutes here. This is important. And that's kind of interesting. And so is this, actually. A couple of cute videos. We'll get back to this one. Yeah, so this is, we have a 3D printer, and it's got this long spool of plastic, and it takes like 8 hours to print things. And they've got a new one where the ink is down in the gel, and you just send in, I think, something that heats it and makes it solidify or something. So, what's that? There's nothing. Oh, wonder what happened. This thing looks like it fell out. Good, thank you. That sort of thing happens. That impairs the brilliance of the experience. And there's still nothing up there. Let's see what's wrong with this thing. The light's on. There it goes. Oh, it worked? Okay, good. All right. And I'll quit fixing it. So let me show you this little video. All right. So they call it a bio printer. I don't know why, but anyway, that's the point. You reach in with a print head, I guess, and just solidify the stuff. I don't know if it's squirting out a solidifying agent or just heating it up to make it solidify, but it is an interesting idea. And of course, you know, people are 3D printing houses, they're 3D printing human organs for transplant and all sorts of good stuff. So there's going to be a lot of exciting stuff happening with different kinds of 3D printers, and that'll be another type to add to the mix. This one I thought was pretty good. This is, I think, Mercedes-Benz, the new windshield wipers. There's the old-fashioned windshield wipers, spray junk in front of you so you can't see just when you're trying to see, which is, in fact, pretty annoying, I must have to admit. And they say, you know, we don't have to do that. So instead, they put little tiny nozzles in the wiper. So it squirts the water just like a 1/4 inch before the wiper hits it. So the water goes away right away and it isn't blocking your vision, which is pretty brilliant, actually. And not super high tech. And it's one of those things, I wonder why nobody did this 30 years ago. That seems like a pretty good idea. I want it. Because I have a problem with windshield wipers. They irritate me, especially around here when you drive into the sun. Anyway, so this is pretty cute. Why do you bother squirting the water anywhere except right there? That's the only place it matters. So anyway, that's intelligent technology. All right, let's see if I can somehow get this thing out of my way. All right. I wonder if I can move it off. Oh, okay, can't get it very far out of my way. I'll have to get used to it. All right, this will affect a lot of people. CCleaner, and they haven't had any explanation yet. In fact, I haven't even seen much of a statement from the people that made CCleaner, but Cisco, their researchers found that CCleaner, the official version downloaded from the official manufacturer's site, was poisoned with malware for a month before they noticed. And it is signed with their developer certificate in good order. So apparently either they've been hacked or they've got a malicious insider or somebody poisoned the tools they used to build it. All those things have happened before. Nobody really knows. But for a whole month, everybody downloading CCleaner was infected. CCleaner has some enormous number of users, like 1 billion. So they said there's like 3 million people they know are using the infected versions. So that's pretty harsh. And the backdoor is collecting information, sending it back to command and control servers and doing all the rotten things. They've already downloaded some versions and pushed out an update, a notification to update for some users. One thing they say is that they didn't say whether they've used the same digital certificate to sign the new versions. I was thinking that wouldn't be too hard to test, and that would be interesting if they did, because obviously they shouldn't. Anyway, that's an issue. Signatures are not a panacea. All right. Chelsea Manning's out and giving talks various places. I invited her to talk here. She didn't answer. I don't imagine we can compete with the kind of people I have her talking now, but now she was just at Harvard talking to them. She was also at Noisebridge last week, which made me think she might talk here. They didn't announce it until it was over, but she spoke at Noisebridge. And I would imagine that she is not anxious to go to a place where she'll have a bunch of angry people yelling and screaming at her and perhaps committing violence against her, which I certainly, there are plenty of people that want to do that, no doubt. So I invited her here. I said we could keep it a small, low-key, unannounced affair if you want, or we can make a big thing and advertise it. But I think she's probably got a lot of big shots competing for her attention. But anyway, they invited her to come speak as a fellow at Harvard, and then then they got requested from CIA agents to not do that. They took her back her fellowship. And she claims it's the government abusing her, and there's some truth in that. And of course, Harvard's point of view is these CIA agents were Harvard students and Harvard alumni, which they probably are too. But anyway, it's a very controversial figure, and I would like to give people a chance to hear what she has to say. I finally, by the way, they had these Patriots rally in Berkeley, which is going to have the right-wingers come, and they were having all kinds of argument with management about whether they can do it. And I guess I finally realized why we couldn't have the Cyber Patriots competition this summer. We tried to have Cyber Patriots, and the San Francisco High School District said, oh no, we can't possibly have anything with Patriot in the name. So he changed the name to Cyber Camp and had the event, and had to sort of remove the Patriot, which is the original name. It was developed by the airport, but now I'm beginning to understand why Patriots is a dirty word. If you show 10 San Francisco parents some kind of Patriot event, 8 of them are going to assume it's an alt-right event. And I can see why they would say, my kid isn't going to that. Are you nuts? So they've kind of co-opted that word. Anyway, let's see if there's anything else hot.
I got a question on
Yeah.
Annie.
Annie?
So when she exfiltrated that data, was there anything special?
Annie? You mean Chelsea?
Yeah, Chelsea.
Right. Yeah. Well, as far as I know, there was nothing super special about it. She burned it to a Lady Gaga DVD and snuck it out physically to get it out of the CIA's build, or out of whatever military building it was in, which I think was CIA or NSA, and then sent it, I think, through the usual online system to submit it to WikiLeaks, but I'm not sure. Yeah.
I know for the military, the such thing as a duty to disobey an unlawful order.
Yes. As far as her legal status, I think she had not a leg to stand on. I mean, she was on duty military and totally leaked classified information. Therefore, he went to jail. I mean, and I think there's no lawyer that could do anything about that. Just President Obama pardoned her towards the end of his office. Other than that, she was in military and solitary confinement, not getting the medical care she needed, sort of being treated with total contempt and disrespect, which is what tends to happen. But I mean, as far as her legal position, I think she had not a leg to stand on.
Wait, really? Because like if I'm in the military,
yeah,
my commanding officer says, "I need you to blow up this footage."
Sure.
For a certain reason,
yeah.
I'm allowed to say, "Are you sure you're asking me to do an illegal act?"
Yeah, you're right. That is, in theory, you can defend yourself in the military in that the orders you were given were illegal, but she didn't succeed with that defense, and I don't think she'd have much chance with that defense, because her position was basically that our standard routine military operations are illegal and intolerable. And the main thing that led to it, I think, was this drone or something in Afghanistan or Iraq that was blowing away journalists. That was the main one. I'm sure that, and I remember the same kind of thing happened in Vietnam back when we didn't have videos, and there were arguments. I think the stuff that she leaked was not the kind of thing that could possibly win that argument, and it didn't win. But on the other hand, I think that's mostly a fiction, that on-duty military can get away with disobeying orders with an argument like that. I think that's not how it works. I think that's, has anybody ever gotten away with that defense? I don't think so. I mean, once you're in the military, you don't have rights. You don't have a proper trial. You don't have an attorney that comes to protect you as usual. So the odds of actually convincing all those people who are basically military members that you were okay not obeying orders is very hard. I think it's largely a fiction. Yeah.
I think she was entrapped by Adrian Lama, who was working for the feds trying to get out of it.
Adrian Lamo is another important character in the drama. Absolutely. Adrian Lamo, she confessed this to Adrian Lamo, and Adrian Lamo promised to keep it secret and then betrayed her. And his point was, he had the attitude probably like all the people in the military, this is a terrible thing, should have never been leaked, I really got to stop it. So he feels like he did the right thing. She feels like she did the right thing. I'm sure the military that locked her up felt like we were doing the right thing, and they all have good arguments. It's, that's why I'd like to hear the story. I'm not trying to come down on one side or the other. It's an important episode of cybersecurity. Anyway, but I'm mad. My impression is that she's not yet really ready to talk on the record about it. So maybe get to see her talk about it at DEF CON or something. Anyway, so we're up to DES here. And here's the game. Oh, I think, I think before I start this, I just want to do a bit of review of the math, because you guys hopefully have learned your modular arithmetic, and I'm just going to go through it again, give you a little bit of practice. So remember, you got, because this is going to come back, this is really important in cryptography. So if you have modulus 9, you only have 9 symbols from 0 to 8, so 14 mod 9 is 5, because it's 9 plus 5, and the general algorithm is you divide by the modulus and keep the remainder. So 22 mod 9 is 3, 34 mod 9 is 7, because 9 times 3 is 27, and you are 7 beyond that. 35 mod 9 is 8, and the easiest way to get there is 36 as an integral multiple, and what you're left with is -1, and -1 just means go the other way around the circle from 0 back to 8. So hopefully that's not too hard. So if you got modulus 4, you have 5 mod 4 is 1, 12 mod 4 is 0, 13 mod 4 is 1 again, because it's 1 more than an integral multiple of 4. 13 is 3 whole times around and 1 more from 0.
So is 1 mod 4 equivalent or equal to 5 mod 4?
1 mod 4 is equal to 5 mod 4. There's an infinite number of numbers that are all the same modulus. 1, 5, 9, 13. All those numbers are identical in modular arithmetic. That's the whole point of it. Instead of having a number line that goes to infinity, you just have a ring that goes around and around. There are only so many values. And that's why things like, when you keep adding numbers, they get too big and they overflow the number of bytes, but that never happens with modular arithmetic. It's only this big and it will never get any bigger. It just rolls around like an odometer. And that's real important for cryptography. So here's mod 6. 5 mod 6 is 5. 6 mod 6 is 0. 7 mod 6 is 1. Hopefully it's clear enough. And in Python, you do it with the percent. So I'm just going to run those Cahoots again just to reassure me that everybody's got it. Because we're going to eventually get to inverse numbers in modular arithmetic, but not today. But I want to make sure people have got it forwards first. All right. So this thing should be set. Good, with reasonable defaults. Good. And I see we got 11 online people. That's good. And they tell me you have a fair chance to win the Cahoots here, too. 233 132. Oh, there's an attendance list. I'll pass it around after this. Good. I see Artyom's on. Must be virtually. Woot. I think I've seen that before. Okay, good. 16. I'll wait a few more seconds to see if we have more. 11 online, and I think I got at least 11 here. I'd expect a few more. There may be Kahoot abstainers. I know when I used to use the iClickers, there were a couple students that just refused to use them. They didn't like it. So you're certainly not required to do this. It's just extra credit if you like it. All right. Wait a few more seconds, and then we're going. All right. So what's 6 mod 9? All right, it's 6. Good, everyone got it. All right. What's 12 mod 9? Good, everyone gets it fast. Glad to see it. That's 3. Good, that's what I was hoping you guys get good at. 9 mod 6. There they come. All right, good. Pretty much everybody's getting it right. That's what I was hoping. 4 plus 21, mod 9. All right, that's 7. Oh, it's less than unanimous because 4 mod 9 is 4 and 21 mod 9 is 3 because it's 18 plus 3. So you add 4 plus 3. That's one way to get there. What's 901 mod 9? Okay, good. Everybody knows it's 1. I think there's one more. There you go. 4 minus 256 mod 16. Okay, 256 is an integral multiple of 16, and negative 256 is also an integral multiple of 16. So this is 0, and the answer is 4. All right. All right. Anyway, I'm good. I'm glad to see people are getting pretty good at it. That will make it hopefully less confusing when next time we get into the reversing. So Artyom, NH, and Mahmoud. I know who Artyom and Mahmoud are. NH will have to tell me who they are to get points, but we'll see if there are more Kahoot winners later. The same people may win again. All right, good. So that's it for modular stuff. And I ought to mention that there are binary games available for extra credit in this class, and I've been adding more of them, and I will be adding more of them. So down here is binary games, and you do these until you get 10 in a row, and I finally added like a winning screen, so it isn't going to keep asking you 11, 12, 13. I had people getting up to like 50 and then emailing me, when do I win? Anyway, so nibbles, bytes, and hex, modular arithmetic is here, and also XOR, which I'll talk about tonight. So, and there will be more of these. The modular arithmetic 2 is going to be the inverses, which people did not like the first day, and I want to get there by stages. So more people like it, and we'll probably have some more stuff there too. All right, so we're going to talk about DES, which is the first government-approved crypto system for general purpose. It is now debunked, disgraced, and not secure anymore, but triple DES, which was the emergency replacement, is still considered perfectly fine. The only thing wrong with triple DES is it's kind of slow to compute. AES is faster on modern equipment. But if you are using triple DES, there is no particular reason to rush to anything better. Triple DES is fine, but single DES is toast. But it's important to understand it so you understand the things that came after it. So we're down here in block ciphers, which are a subset of symmetric ciphers. We have not touched public key encryption in any depth in this class yet, and we haven't touched stream ciphers in any depth. This is block ciphers. They all work with a block of input data, which in practice, all the block ciphers I know have either 64 bits or 128 bits as the block. You could have any size, but those seem to be the only ones that are popular these days. So before 1972, cryptography was considered a military secret, and the government did not approve it for use by anybody else. As you know, the FBI still doesn't really appreciate that we can encrypt our cell phones to where even the cops can't get in. That seems like they don't think we have any reason to do that. And certainly back before the 70s, they really didn't think anybody should be using cryptography except the military. But by 1972, people were using computers at banks, and those computers were starting to be networked. And people began to understand that you really have to have strong cryptography available in the private sector. But the same military that doesn't want us to be able to hide things from them today didn't want us to hide them. So they had a bunch of submissions. IBM proposed Lucifer, which would be fine today, an unbreakable 128-bit cipher. The National Bureau of Standards secretly asked the NSA to test it because at that time, the NSA had a lot of advanced cryptography knowledge that was not known outside the military's secrecy, and I believe that's still to be true. I mean, as I said before, my personal belief is that they have a working quantum computer, because about a year ago, they suddenly issued an emergency warning about quantum computers, and I've been watching through the years. When the government has an emergency warning, they're usually warning you because they got one. But anyway, in general, it's pretty much well established that the NSA has 20 years ahead cryptography that is hidden behind the military secrecy, and the public, lots of us outside here don't get it until 20 years later when some mathematician invents it again. And that is, of course, their job. They should also have kinetic weapons that are way ahead of whatever you can buy here in way of weapons. That is their job, to be on the forefront of this stuff. So anyway, the NSA had the technique of differential cryptanalysis, which is an analytical technique which was not known in the public sector then, but then the DES was made resistant to that analysis, which means they made it actually stronger than people that were without a security clearance could have made it, but then they weakened it by shortening the key, which was, no one has ever explained why this happened, but we have all guessed, and the logical guess is they made it strong so nobody could solve it analytically because that would let everybody in. And they made the key a length so that they could get in with their supercomputers, but nothing you could buy on the unclassified side was powerful enough to get in. What they always want is this thing called no bus, nobody but us. They want a backdoor that the government can use that nobody else can use. And they try to make it. And this is one way to do it. Make the key long enough that nobody except them can brute force it. That's what they did. And so differential cryptanalysis is where you make an approximation of the algorithm as a linear function, and you try to make an approximate version of the algorithm that has a more than 50% chance of being right. And then encrypting a large number of plain texts will give you some information about the key because you're able to figure out some relationship between the ciphertext and the key. This is what's wrong with stream ciphers like RC4. It's not completely white. One byte pattern is more likely than anything else. So by encrypting a large number of plain text, you can find a pattern between the plain text and the output, which reveals something about the key. Anyway, that's the game here. I'm not going to go into it in any more detail. I don't really know any more detail than that, but this is the attack that DES stops.
So,
yeah.
P minus, is that probability minus?
Yeah, probability minus half. Yeah. So if you get a 60% correct prediction, you need about 100 encryptions to do something about the key. In practice, you get a much smaller thing. I know with RC4, the offset is like 1 in a million. You know, it's 0.500001 probability, and that's still enough to crack the key with something like 100 billion encryptions. And that's the problem. Even if you need 1 billion cycles, you can really do that, not too long on modern equipment. All right, so DES encrypts blocks of 64 bits, was approved in 1977 by the NBS, which is later became NIST. This has been popular for 30 years. It's a symmetric algorithm. The main problem with it is the 56-bit key. That means you can just do it by brute force, and therefore no amount of brilliance will save you, but triple DES is fine. If you just use 3 rounds of DES with different keys, or even 2 different keys, not necessarily 3 different keys, you come up with something that there is no known way to get in without the key. You end up with an effective key length of 112 bits, and that's enough that nobody can get in. So 56 bits was brute forced in the 90s, and 64 bits was brute forced after that, and a 72-bit brute forcing project is underway and is expected to take 1,000 years to get into a 72-bit key. So anything significantly longer than 72 is essentially uncrackable by brute force. The only way you're going to get in is if there is some kind of shortcut. And the shortcut, that's what these analytical techniques are. You do some kind of analytical mathematics to find a way to zero in on the key without trying them all. And according to the, I went to the Cloudflare Summit, and they had some cryptographers there from big shot places like UC Berkeley, and they were talking about quantum cryptography. They're trying to get one of them to come here to give a talk. We may have him visiting in this class. But anyway, what he said is, the thing to understand about quantum cryptography is quantum cryptography does not do 2 to the 128 operations. Quantum cryptography makes it possible to find the answer by doing less, like 2 to the 64 operations. And that's the point. Quantum cryptography will be able to crack 128-bit key, apparently. But we will see there's no device available anywhere that can do that yet, as far as we know. But there are prototype devices that can have like 2 or 4 qubits and that cost $1 million out there, suggesting that in a few decades, these things might get miniaturized and improved to where they can do that. Anyway, so AES is what's recommended now since the year 2000. That is much better with 128-bit key, 192 or 256. And we'll go over the details of AES the next chapter. But here we're talking about DES, and here's some important concepts. Claude Shannon invented a lot of this. He invented information theory for computers, which helps you understand what's going on in cryptography and a lot of other things. So confusion and diffusion are 2 desirable properties of a crypto system. And confusion means you cannot find a relationship between the key and the ciphertext. So you can't analyze the ciphertext and find some pattern and deduce something about the key, which, as I mentioned, is what's commonly going on. Substitution is what does that. And we've done letter substitution before, just plain old alphabetic substitution in the last chapter where you take A and turn it into B and B and turn it into C. And that means the ciphertext no longer appears to have any relationship to the plain text. It's not very perfect because frequency analysis gets in, but it does confuse the relationship there. Diffusion is where if you change one plain text symbol, you'll change all the ciphertext symbols. So it smears it all out. So otherwise, some patterns of input are preserved in the output. And this is where I might as well mention, in about 2 chapters, we're going to get to the modes. And I'll show you this project I just added here, Project 8, ECB versus CBC mode, is a good example of that. If you start with this image and you encrypt it in ECB mode, you get that image. And the reason you do is because it's electronic codebook. If you have a block of input, it turns into a block of output. So I have a block here that's all black. It turns into some color. The next block is also all black. It just turns into the same color. Next block is also black. It turns into the same color. So even though you have a AES, this is a perfectly good algorithm, because you're using it incorrectly, you have not removed all the patterns and you can still see the image. So this is not what most people would regard as encryption. You have not hidden the secret and all that well. Proper encryption is CBC mode, which we'll talk about, and that turns it into this, which is what you expect when you encrypt something. There should be just random noise so that all the bits in the original image that had a pattern are now smeared all over the place. So you cannot tell what part was dark and what part was light anymore by looking at this. That's what you want. And the technical term for that property is diffusion, where you smear out stuff. All right. And bit permutation is what we use for this, where you rotate the bits around, which you'll see. So there are confusion-only ciphers. The seizure cipher and the substitution cipher have confusion, but they don't have diffusion. But diffusion-only ciphers also exist, and they're also insecure. So the real secure ciphers are ones that have rounds that include both confusion and diffusion. So you mix it one way and you mix it the other way, and you do several rounds of that, and that's what, in practice, makes something that is very hard to crack. Yeah?
Just curious for databases.
Yeah.
Tend to use diffusion
Well, in databases, I know one issue they have is hashing, where you hash things just so you're not constantly going to the same record, just to smear things out. And that's a similar issue, and I think that would be diffusion. I'm just guessing. That seems what it's like, yeah. But it's, I know hashing in databases is a big issue, where you want to have a key that's sort of like load balancing, has an equal chance of hitting any of the results. That seems like diffusion to me. But they don't use that word there, but it's probably similar. There are often many different words for the same thing. Like if you add one way to prevent this thing where the patterns in the input are produced in the output is to add something random before you encrypt it. And that is sometimes called a nonce, and sometimes called a salt, and sometimes called a seed. And they're all close, very similar things. Anyway, all right, so here's how a product cipher works, and this is how they all pretty much work. You have diffusion one, then a round of confusion, then another round of diffusion and confusion, and another round of diffusion and confusion until you've done a lot of rounds, like 16 or so. And then you've scrambled things here, so it's really hard to undo without knowledge of the key. And that's the point. And the result is, if you have good diffusion, then changing one bit of the key will change half the bits in the output. They'll all change. And you can test this with AES. And this is where like I say, in the book, they go into the mathematical details quite a bit more than I plan to do. I don't really care that much about the details of the math. I just care about using it. So you should have Python available. I think you've been using it in the classes, in the projects. You can install it on any OS. It doesn't need to be anything fancy. You start Python like that. In fact, most of this class, we're not even going to write scripts. We're just going to do it right here in immediate mode. All right. So because right here you can do simple calculations. So it's from crypto.cipher import. You can start using it. Like I say, you do not need to know every detail of how it works to use it. Import AES. All right. Now you need a key. The key has to be 16 bytes if you're the most common kind of AES. So I'm just going to make a key of, say, A, B, 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 C, 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 D, 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 and that's not hexadecimal. It's ASCII. These are full bytes. So that's an acceptable key. Now I have to have a message, and the message also has to be 16 bytes. So it's hello there, and then some dots. Let's see, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. I think that's 16 bytes. It's got to be exactly 16 bytes or it's going to crap out on me. We'll see what it does. Now I can do Cipher. This is what prepares it. It's AES.new. This creates a new Cipher object that's going to do AES. And you can give it several parameters, but if I only give it a key, it chooses the simplest mode, which is ECB mode, electronic codebook mode, the one that leaves patterns in the input. But you can do it this way, and now you can just do Cipher encrypt of anything you want. I'm going to encrypt my message, and it worked. Now it printed it. What it tried to do was it created random bytes for all practical purposes, and it tried to print them. So some of them are printable, like pound and parentheses, and some of them were not printable. So it had to put them as like \x1c. So to make something a little easier to read, it's better to do encode as hex. Then it will just give up printing it as printable characters and just print it in hex. So there is the 128-bit output that is my scrambled message. And now what I wanted to test here is for diffusion and confusion. So let's change the key. Here's my key. Okay, I'm going to change that from D to E, which is only going to change 1 or 2 bits of the key. Now I'm going to make a new object based on the new key. And then I'm going to encrypt my message again. And you can see C81FE74, no resemblance anywhere. This encrypted stuff doesn't have any resemblance to that encrypted stuff, and that means we have good diffusion. Even changing one little bit of the key just scrambles it all up. If changing 1 bit of the key changed just a little portion of the results, then you could deduce the key from patterns in the results, and that would be a bad crypto system. So, like I say, it's good to see that it works. And how easy it is to do AES in Python, which is why we're doing it. You really don't need a special tool. You don't even need that crypt tool, Windows tool. It just takes a few lines of code to do it. Yeah.
For the image encoding, I'm confused with one thing.
Yeah.
Would it be better for one image to be huge, or for you to split up that image into multiple times so you have a cipher going that many times?
I'll repeat the question for the online people. He's asking whether an image should be broken up into pieces and encrypted separately, or encrypted as one large file. And it's perfectly fine to encrypt it as one large file. Because that's the point about AES. It's a very good crypto system. Even if you have a lot of data, all encrypted with the same key, there is no known procedure where that tells you anything. You would think there'd be. For example, that's the problem with RC4. That's the problem with WEP encryption. If you have a lot of stuff encrypted with the same key, there's patterns you can deduce the key. But as far as I know, there is nothing to worry about there. There are some systems. That was what WPA1 was. WEP had a defect where if you encrypted thousands of packets with the same key, you could deduce the key. So WPA just changed the key for every packet, so you wouldn't get too many. So that's a patch you can put on a weak crypto system, but I don't think there's any reason to do it for DES or AES as far as I know. Certainly not AES. This is an important question, and just the kind of stuff we should be thinking about, in my opinion, how to use it and what are the risks. So here's, like I say, just changed the last bit in mine when I went from B to C. All right. So DES in Python is here. That was AES, right? Yeah, so let's use DES. It's the same old story from Crypto Cipher. Import DES. It's all just right there for you. Only now everything's 8 bits. So I can put in a key of 1, 2, 3, 4, 5, 6, 7, 8. And I can put in, whoa, what did, oh, I forgot an equal sign, didn't I? All right, key equals that. Then I can have a message equals a secret. That's 8 characters. DES was an 8-bit system, it works. So then I can do cipher equals DES, a new object based on that key. Got to spell it right though. And then I can do cipher encrypt of my message. Okay, and again, it's kind of hard to read. It would be better to just encode it in hex. Okay, so there's the key, there's the encrypted stuff. And if I just want to change my key to putting a C there, that'll put one more bit of 1 in there. Now I create a new DES object with that key, and I encrypt it. And now I get exactly the same result. So here we come across something horrible about DES. Remember, how long is this key? 8 bytes, right? How many bits? How many bits? 64. How many bits are the key in DES? 56. It doesn't use all these bits. And instead of just taking 7 letters or something, what it does is it ignores the last bit in each byte. And the difference between a B and a C is the last bit. Let's take a look at that. If I do B, and how do I turn it into binary? I think it's on the next slide. I've forgotten. Yeah, bin of, okay, bin of ord of B. Ord of B will get me the numerical equivalent, and bin will turn it into binary. So there's B, and here's C. Okay, so the only difference between B and C is the last bit, and DES ignores the last bit. So how rude. So you think you changed the key, but you didn't change the key. If you want to change the key, you got to go from B up to D. Now that changes a couple bits. So as a matter of fact, yeah, that'll do. So let's go from B to D. So let's try that again. If I do cipher encrypt, this is the way it was. Now if I change the key to D, make a new cipher object, and encrypt it again. Now I get completely different results. BE52, 42 on this, 4407. That's what you want. Proper diffusion. DES has good diffusion, but it's only using 56 bits, which is kind of screwy. All right. So that's the game there. DES does have these good properties. All right. So here's the algorithm. You have some initial permutation, then you have 16 rounds of encryption, and then a final permutation. The block size is 64 bits, but the key size is only 56 bits. And that's the game. What it does is it takes the main key and it creates 16 round keys, K1 through K16, and uses a different key for each of these things. But the keys are not really different. Well, they're different, but they're all based on the original key, which all they're really doing is rotating the bits around of the original key. So I got some cahoots about that. That should be here. And I'm going to leave that site. And in fact, I probably need to stop and restart less than a minute. Yes, I'm going to stop and restart the share so that you guys can do the Kahoot remotely. So stop, end meeting.